So everybody should be able to grab a pen and start writing.
Oh, no, but not rectangle, not rectangle.
Can you still hear me, Justin?
Yeah, I can. I put headphones on, so I look kind of weird, but it's working.
Okay, good. So everybody can hear me and we're ready to go. Okay.
Yep.
So if we're going to use U-Substitution, or if we're going to use integration by parts here, then we have to make a choice for U, and before you guys got here, Kiera suggested that we use X. That means that du would be dx. Then we know that dv has to make up the rest. Let me draw a little connector here. U times dv has to make up everything that you see here in the integral. So u is x and dv is the rest. Okay. So if dv is e to the negative 2x dx, then v, well, we have to figure out what v would be. Who's that? Good. Yeah. If we let v be negative 1/2 e to the negative 2x, then we could check, and we won't take the time to check, but if we did and we took the derivative of what we've called v, we would get e to the negative 2x dx. Okay. So let's see if that makes our life any easier. So the integration by parts says that this can be rewritten as u times v, so that's x times negative 1/2 e to the negative 2x. So we'll just put the negative 1/2 out in front. X e to the negative 2x. That would be minus the integral of v du. So v is negative 1/2 e to the negative 2x dx. Okay. So that's looking pretty good, because this first integral had pretty much this, but multiplied by x. And this is just this times a constant, and constants, we've been taking integrals long enough to know that constants are easy to deal with. Okay. And to make it a little easier to look at, we'll do that thing that makes constants so easy to deal with and bring it outside the integral. So that has to be a positive 1/2 integral of e to the negative 2x dx. Okay. Maybe to do this integral, I don't know, I'll ask you guys what would be the way that you would take the integral of e to the negative 2x dx.
About like integration rules as of 8.1.
Sure, yeah, you could look there. That would definitely be a good place to look.
Well, then number 6, e to the u would be perfect.
It would almost be completely perfect. We just need, if you notice, it says e to the u du. So we would need this to be du instead of just dx. You're on the right track. We just need to maybe mess with it a little bit. So if we get rid of that dx and maybe just move it over to here, there's something we could squeeze in there so that all of this together is du. Oops. Try not to change the pages. Everybody's pages change. It's okay. So if we're going to use number 6, which is e to the integral of e to the u du, here's our e, here's u, so that makes things easy if we can spot what u is, and this needs to be du. Good. Negative 2 dx is the derivative of negative 2x. Okay, but so now we have to kind of fix this. We can't just throw a negative 2 in there and not balance it out somehow. So how are we going to balance out that negative 2?
Adding a positive 2 plus 2?
Well, it's multiplied by negative 2. Put a 1/2 out here. That's good. I'm going to scroll down.
Okay, so is it 1/2 integral of e to the negative 2x negative 2?
Well,
dx?
we already had a 1/2 out here. We already have a 1/2 out here. And we want to put another 1/2 out here to balance out this negative 2. Actually, this should be a negative 1/2 to balance out the negative 2.
Okay, that makes more sense.
Okay. So we'll rewrite this as negative 1/2 x e to the negative 2. I think I wrote that wrong to start with. That should be negative 2x. Minus 1/4, because we got this negative 1/2 times this positive 1/2, so you have negative 1/4, times the integral of e to the u du. So what if we follow the pattern of number 6 on page 520? What would the integral of e to the u du be? Almost, except we don't need this negative 2. If you look at rule number plus c, good. So for this part, if you look at number 6 on page 520, the integral of e to the u du is e to the u. So I don't know if you can hear Leora, but she's just walking around talking on a quote phone. So yes, this is e to the u times du, and so e to the u is the integral. And so altogether, negative 1/2 x e to the negative 2x minus 1/4 e to the negative 2x.
Question, Mr. Stewart.
Yes.
What is my eraser function on here?
Remember you had to grab that black arrow at the top above the pencil and select things
Okay, so
with a box and then press delete.
Okay, much better. Thank you.
Yeah. Okay. Alright. So that's it. That's number 11. So integration by parts was a good choice, and the u being x was a good choice. It all worked out. Alright. So if you have any questions, go ahead, or if you have another problem you want to start on, go ahead with that too.
Number 15. Does that work?
I think so. Number 15. So now we have to decide, do we use integration by parts, or is this maybe a function that we use older integration strategies for?
That's number 15, because I have 15 as being completely different.
That's because I'm looking at 15 from 8.1.
There you go.
Alright. Alright. Squared e to the x to the third. But still, the same question. Do we use integration by parts, or can we make it fit an old formula? Okay, that's Logan, so what would you make u be equal to? X to the third, good. So if u is x to the third, then du is 2x dx. So let's see what we can do here. What am I doing? 3x squared dx. That's right. That was the right correction. 3x squared dx. So we've got e to the u, and then we have almost du. We have x squared dx, but our du has a 3 that we don't need, so we're just going to divide 3. Good. Take that 1/3 outside, and now we'll have e to the u du. So we have 1/3 times, what's the integral of e to the u du? Anybody can jump in there and write it down. Yes, 1/3 e to the x to the third. And that'll do it. That's it, yeah. U is x to the third, du is 3x squared dx. And we are able to write this in the form of one of those formulas on page 520. It's number 6, I think. And so that works. If it fits that old formula, then use it.
So would this be considered integration by parts?
No, integration by parts is where you have u and du, and then you pick your dv and your v. So I guess in short, integration by parts has u and v, and dv and du. $17. Let's see, I got a lot more room here. Let's do 17 here. So I just scrolled down below 15 to do 17. T times the natural log of t plus 1 dt. Now, there's something that's like a dead giveaway here for integration by parts. Can you spot what that is? Yes, the natural log. Because if you look at all of the formulas on page 520, you won't find a single one that has the natural log in it. So you know that it's going to be integration by parts. So now we have to start picking our u, and then when we know that, we can find du, and whatever u isn't, dv will be the leftovers, and then we'll find our v based off of that. So what might u be? Okay, t plus 1. So then what would du be? dt. Okay. So then what would dv be? I think there's a couple things that we're missing here. Natural log of t plus 1, it's not multiplication. You're not multiplying the natural log times t plus 1. You're taking the natural log of t plus 1. So a couple things about, a couple of reminders about integration by parts. Let me pick another color. Remember that we're trying to set it up so that we're taking the integral of u times dv. So we're trying to take the integral of u times dv. So we want to break this up into two functions, so that part of it is u and part of it is dv, and u times dv is the whole integral. So the thing of making u be equal to like the inside function, that's more of a U-substitution way of thinking. Well, the natural log does need to stay with the t plus 1, yeah. You can't just pull them apart, natural log over here and t plus 1 over there. Okay.
So would the derivative of u be the natural log of t?
The derivative of u be the natural log of t? It depends on what u is. We have to choose a u.
Was t plus 1 not correct?
Well, if we let u be t plus 1, then the derivative of t plus 1 would be dt. Just like we said before. But now it just comes down to, then what is dv? dv could be t, but then you see how u times dv does not make up the integral. The entire integral needs to be made up by u times dv. Here's what we're trying to do. Get the integral of u times dv and set that equal to, well, this is the formula that we derived in class. U times v minus the integral of v du. So we're trying to get a function times a function to kind of take the place of our original integral. So making u equal to t plus 1, really no matter what you choose for dv, it's just not going to happen that way. You're not going to be able to make u dv, u times dv, be equal to this whole thing. Why don't I just, I'll show you what I would do, and I'll just keep this bottom red formula over here. And so if we let u be equal to the natural log of t plus 1, then what would the derivative of that be? would be 1 over t plus 1. Okay, and if natural log of t plus 1 is u, then what is dv? You know, what are the leftovers of that integral? Right. And then the antiderivative of t dt, what would that be? Yeah, I'm just going to fix this a little bit. 1 over 2 times t squared. Because if we take the derivative of 1/2 t squared, we would get t dt. So, I'm just going to erase this now. So integration by parts says that this is the same as u times v, that would be the natural log of t plus 1 times 1/2 times t squared, that's u times v, minus the integral of v du. So our v will be 1/2 t squared du is 1 over t plus 1. And this, I guess, this should have, no, let's see, this should have a dt. So there comes our dt. Alright. Now we have to take the integral of t squared over t plus 1 dt. Long division, yeah, very good, because this is a kind of what we would call an improper rational expression, and so for this part we would use it's not gross, it's not you. We'll just use long division really quick, we'll get it over with. So what do we multiply t by to get t squared? Why don't you just fill that in up there? Yep. Yeah, just t, right? Because t times t will be t squared. So there's no question about it. And so what we do next is take t and multiply it by this whole thing, multiply by t plus 1. So t times t is t squared, and t times 1 is t, and we subtract. T squared minus t squared is 0, and 0 minus t is negative t. And now we say, what do we multiply t by to get negative t? Negative 1. So negative 1 times t is negative t, and negative 1 times 1 is negative 1. So we subtract like before. Negative t minus negative t is 0, and 0 minus a negative 1 is a positive 1. So that's our remainder, remainder 1. I'm just going to scroll down here, make some more room. So let's just get rid of, well, let's not get rid of it. Question, Justin?
Yeah, so was the long division really necessary?
Yeah, because what we're about to do is rewrite this using what we just did with our long division.
We couldn't have left it at t squared over t plus 1.
Well, we could if you could tell me how to find the integral of that.
Oh, well, I can't, so.
But we're going to use the long division results to make taking this integral not too difficult. Okay. So I'm just going to fill all this in because it'll just make me feel better. Alright, and so this stays the same. We're using long division to rewrite that integral that we just made with integration by parts. Times the integral of... Now we just took t plus 1 and divided it into t squared with our long division, and it came out to be the same as t minus 1 plus 1, our remainder, over t plus 1, our original divisor. And then this all get a dt. And so now we get to have three separate integrals, this one, and this one, all of which are pretty easy to find. So the integral of t dt minus the integral of 1 dt plus the integral of dt over t plus 1. Alright, so let's just kind of underline that one in red, and then somebody in red write the integral of t dt, and then in blue we'll write the integral of 1 dt, and in bright green we'll write the integral of dt over t plus 1. Anybody for the integral of 1 dt? Okay. Oh, there it comes. Good. T. The derivative of t is dt, so t is the antiderivative of dt. It was supposed to be blue. I'll fix it. Sort of. Oh, okay, we both fixed it. So minus t. Good. Somebody's working on the green one. Very good. Excellent. And if you felt tired after all that, then you could just leave it. You wouldn't have to simplify it anymore. That would be just fine. Very good. Is that Justin? Trademark Justin. Okay, so you want to review that one, or have any questions on that one, or do you want to go on to the next one? 13. I'm going to move down below what we just finished and do 13 there. I should have started something else. X to the third, e to the x dx. Alright. So, see Kira's writing something. Or not. Or maybe she is. Okay. So what would be nice is if we could make this fit the number 6 formula from page 520, e to the u du. Is that going to work out? No, it's not. Because if it did work out, then let's use a different color. We'll use the color blue for alternate universe. If this was going to work out, and let's say we had e to the x, then this would need to be dx, because it needs to be the derivative of the exponent. Or, if this were e to some exponent and x to the third were the derivative, or the rest of it, e to the third dx, then this exponent here for e would, when you take the derivative, have to be something in the neighborhood of x to the third, like maybe x to the fourth. That would be good, because when we take the derivative of that, it would just be 4x to the third, and then we could adjust with the constant. But neither of these things is happening. This is what we have. So it doesn't look like it's going to fit any of those old formulas, and so that tells us it's probably time to go with integration by parts. So that means we have to take a u and then determine du, then dv is going to be what's not u, the leftover from u, and then we find our v. Okay, remember what we decided in class? The best thing to do is choose a u, so that when you take the derivative of u, it's a simpler function than it was before. So, what would be our choice for u? Good, x to the third. So then, du would be what? Good. So if x to the third is u, then dv has to be the rest. What's the rest? Alright, dx, good. And then the antiderivative of e to the x dx is just itself. That's the amazing thing about e to the x. Amazing. So uv, that's integration by parts right there. So u v minus the integral of v du. Let's put the 3 out here. X squared dx. Okay, so now it might seem like we haven't gotten anywhere. Oh good, a dx over there is important. It might seem like we've gotten nowhere, but look at our original function. It had an x to the third. This one has an x squared. Imagine if we did something similar. We'd then have an x. If we did it again, then we'd have no x's. So good news, we're on the right track. Bad news, that track is a little bit long, but it's going to work out. So let's choose our first u's and dv's and so on were blue. Justin. At least there's no fractions. Let's choose a... where'd my color go? Okay, so like a dark... You're going to have to get rid of that. A dark red U. We'll choose those. And then... But yay, indeed. We'll have to choose dv and v. So, since our first step was encouraging, what's u going to be? Right. X squared, and then du is 2x dx. And then I don't know if you guys has noticed, but if I were to highlight this purple stuff and delete it, it would make automatically my pencil into purple. So maybe color sealer is a little harsh. Okay, so our u is x squared, so a dv has to be what? I don't know that you guys are ready to go when you write dv. Yeah. Oh, look at that. It's all going on at once. So our dv is e to the x dx, and v is e to the x. So now all of this stuff, I'm outlining it right now, is going to be used to rewrite this integral, but the rest of it is still there. I'm going to scroll down now. So I'm going to try and keep this color coded. We still have this x to the third, e to the third. Is that e to the third? What is that? What did I do? X to the third, e to the x. I'm on a roll today. X to the third, e to the x, minus 3 times, and now this part I'll write in red because it comes from all of this red stuff. This integral gets rewritten using this stuff. So again, we use uv, that's x squared, e to the x, minus the integral of 2x, so I'll put the 2 out here, 2x, there's the x, times e to dx. Okay, so now we do it all over again. Thank you. So now let's choose, because we can see how this is getting simpler and simpler every time. It is taking a while, but it is getting simpler. And so let's choose a green U. And green dv. So I'll make it kind of quick. We've already determined that the x part of it is best for our u, and so the derivative of u is dx, or the derivative of x is dx. dv is e to the x dx, and v is e to the x. And we need an x there. There we go. Okay, so now we still have all this stuff. X to the third, e to the x, minus 3 times x squared, e to the x, minus 2 times. Okay, now all this stuff that we just determined is going to come into play. 2 times this rewritten integral will be our new u times v minus the integral of v du. V is e to the x, and du is just dx, and now we have an integral that we can actually determine. What's the integral of e to the x dx? We've actually been finding it this whole time over and over. Yes, e to the x. Whoa. So this part is just e to the x, and everything else stays the same. So there's when we had to apply integration by parts 3 different times. Justin needs his moments. Alright. You have one more you want to do? It's a fraction. Justin might want to leave the room.
I do not approve of this.
It's okay. I'm gonna pick a different color. Natural log of x squared over x dx. Pardon me. Listen, you can see where this one's going, and it is a little bit tricky. It is fun. All right. So what do you guys think? Old ways from 8.1 and before, or integration by parts? Old, she asks. I'm thinking old, but then if it's old, let's say we use U-Substitution. When we use U-Substitution, it's a little bit different than integration by parts. So we don't have to, you know, make up the whole thing with U and some other thing. We can let U be a piece of it, even the inside of a function, and then du will, you know, be some other part of it. And we just try to make it fit one of those formulas on a 520. Okay, and then what would du be? Oh, just jumped in there. 1 over what? 1 over x. dx. Alright. So now we have the integral of u squared. My wife was getting some juice. They heard you getting juice. So we got u squared there. Can we just put du there? Does that work? Logan says, "Hi, Mrs. Stewart." All right. Yes, it works because u is the natural log of x, du is 1 over x. This is a terrible choice to use red again. Black. Natural log of x is u, and 1 over x dx is du. Yeah, it's kind of messy. But as long as you get the point, that's all that matters. What are we doing? We're fixing it. Okay, fix it. Right. this is collaborative. Yes. Number 4 and 520. Let's see, do we all agree on that one? Yeah, we got u, this would be u to the n times du, because this is the derivative of the natural log of x. Alright, so yes, we've got it right. I'm going to scratch this out. And if this is u, and this is n, and this is du, then let's follow number 4 on 520 and write our integral. Yeah, n is 2. What do you guys think? Right, that would fit the formula. The only part is I'm going to take this out. That needs to be... Now I have to switch my colors again. That needs to be the natural log of x. That whole thing is going to be raised to the 2 plus 1. So that would be the natural log of x cubed over 2 plus 1, which is 3. Missing rest of u. What do you mean by that? Okay. See, if we make all the substitutions. So if we take this, we make all the substitutions, and we call it the integral of u squared du, which it is, then this would be u to the third over 3, and u is the natural log of x. So there you go. So, messy as it is, that's the final product. I guess we could put plus c in there. Make sense? Cool, good. Alright. Did you guys have as much fun as I did? I think it's fun when you guys all jump in there and write at the same time and fill in different stuff, so that's what gets me excited. Alright, well, guess we're done here, and we should, yes, we do get a blue star for our efforts. That's very good. Yeah, that should be it. You guys have any last things? Okay. Well, you guys enjoy your night. I'll see you next week. Good night.